How did you go? Did you work out the problem here with our program? Don't worry if you didn't. Let's take a bit of a look now and see if we can work it out. Righto, jump into the sim and let's take a look. Okay, if our temperature sensor here is sensing 0 degrees, wow, it must be really cold firstly, and our hot water valve is on, or our heat valve is on. So hot water is flowing around the tank and trying to heat up the chocolate. Good. Then, as the chocolate heats up slowly, we get above 60 degrees and the heating valve turns off. Hold on a minute. Did we really get above 60 degrees just then? It doesn't seem right to me because if this slider represents the 0 to 100 degrees that it can detect, wouldn't 60 be somewhere up around here? Not all the way down here? But we wrote the number 60 in here. Something funny is going on, and I don't mean funny haha. Okay, the truth, guys, which you probably already worked out for yourself, is that the number 60 does not represent 60 degrees. It represents 60 parts of, if we bring the slider all the way up, 4,095. So 60 parts of 4,095. Wow, what in the world does that mean? Okay, we need to do a little bit of maths, but don't run away. It's just a little bit, okay? I promise. Just a little bit of maths. Alrighty. So if we are bringing on the heat valve at less than 60 parts of 4,095, that means if we divide 60 by 4,095 and then multiply it by 100, that gives us the actual temperature that the number 60 represents, 1.46 degrees. We are way off. We're almost at freezing. So how do we put the right temperature in here? Okay, what we want in here is the number that represents 60% of 4,095. That's because this temperature sensor measures between 0 and 100 degrees. So we can go 4,095 divided by 100 parts times 60, and that gives us 2,457. That sounds a bit more like it. And if we slide our simulated temperature sensor up to about 2,457, that looks a lot more like 60% of the range to me. Nice. So let's jump out of the sim and fix the number up here, make it 2,457, which represents 60 degrees. And let's fix up the cooling valve operating temp as well, because obviously that's not correct either. So we want 70 degrees, in other words, 70% of 4,095. That will be 4,095 divided by 100 parts times 70, which equals 2,866.5. That's right. Cool. Throw that in and then jump back into the sim. And if we now move our slider, which represents the chocolate temperature in the tank, when the choc temp goes below 60 degrees, the heat valve comes on. And then as we get above 60, the heat valve goes off. And then if it's a hot day and the choc temp goes above 70, this compare function brings on the cool valve to cool down the tank that the chocolate is being mixed in. Awesome, guys. Nice work. Your first program using analogs. Now this time, click Save As and call it choc temp. Cool. Alrighty. Guess what? Yep, I've got extra for you. You didn't think you would get away from me that easy, did you? You should know me by now. The client wants to install a variable speed drive to change the speed of the mixing motor. And they would like to be able to change the speed of the motor by turning a dial. So we would need two things here. We will need an analog input that we can turn, or slide in our case, to adjust the speed, and we will need an analog output that will send the speed reference to the VSD that will be wired to the motor. Now, if you don't know, variable speed drives, or VSDs, as they are commonly known, also known as VFDs, but let's not get too technical, are electrical devices that can be connected to motors to alter the motor's speeds. Think of them for now as an analog output device. We don't need to know too much more for the purpose of this exercise. We just need to focus on our analog output and get that working. But if you are interested in VSDs or VFDs, I have a course on that too, okay? But for now, let's have a break, and I'll catch you in the next lesson where we'll program our analog output to control our mixer speed.